We are nowhere near as close to as smart as we think we are.
We may have to rewrite all the textbooks about the beginning of the universe.
In the ongoing effort to understand the universe's secrets, the James Webb Space Telescope has become a key tool for making new discoveries. But just when we thought we were sure about where the universe came from, the newest discovery from the JWST has surprised us and changed that notion. This groundbreaking discovery challenges the very foundations of our understanding of the Big Bang. But what mysterious events transpired before the universe itself came into existence? Join us as we unveil the first image before the Big Bang captured by the James Webb Space Telescope, the established understanding of the universe. In the past 100 years, scientists have achieved an incredible feat in understanding the universe through the creation of the Standard Model. This model is a detailed plan that explains how our universe has changed and what it looks like right now. It heavily depends on Einstein's theory of relativity and helps us solve the puzzles of how the universe has grown, including its expansion and the creation of huge cosmic structures. In this model, many essential parts play crucial roles in shaping the cosmos. One of these crucial elements is dark energy, which takes the spotlight. Dark energy is a mysterious force that pushes the universe to expand rapidly. Another player is dark matter, a mysterious substance that doesn't interact much with light and ordinary matter, but makes up a significant part of the universe. Alongside these mysterious elements, there is also regular matter, made up of familiar particles like protons and neutrons, forming the foundation of what we normally see and experience in the universe. Exploring the vastness of space, we come across neutrinos, tiny particles with almost no mass and no electric charge. These entities quietly contribute to the complex nature of the cosmos. Moreover, photons, which are basic particles of light, play a vital role in helping us understand how the universe functions. The complex Standard Model acts as a comprehensive tool that enables us to unravel the details of our expansive universe, offering a roadmap to comprehend its evolution, composition, and the mysterious forces that guide its behavior. Around 13.8 billion years ago, the universe emerged from an intensely hot event known as the Big Bang, followed by a rapid expansion phase called cosmic inflation. This initial expansion caused small variations in density, setting the stage for the formation of cosmic structures. However, the century-old Standard Model that has been the foundation of our understanding is now under intense scrutiny. Despite strong evidence supporting it, scientists are starting to question its completeness. Each new piece of data collected by astronomers undergoes careful examination within the existing model to ensure coherence and accuracy. Advancements in technology, such as the James Webb Space Telescope, have provided astronomers with a powerful tool. Paradoxically, these tools are also posing challenges to the established model. The James Webb Space Telescope has transformed our understanding of the early universe, reshaping some of our previous ideas. Let's go back to around 380,000 years after the Big Bang, when neutral atoms began forming in the cosmos. Approximately 550 million years later, a significant event called reionization changed much of the universe into an ionized state. This phase began about 200 million years after the Big Bang, possibly marking the emergence of some of the earliest stars. The JWST, a powerful space telescope, has allowed us to explore deeper into space than ever before, revealing galaxies from incredibly distant realms. This breakthrough provides us with unprecedented insights into the early stages of the universe. Scientists have a widely accepted model called the inflationary hot Big Bang or lambda CDM model, which has successfully explained many fundamental aspects of the universe. This model has helped us understand phenomena such as gravitational lensing, the complex structure of the cosmic web, the evolution of cosmic structures over time, and the movements of galaxies within clusters and groups. Additionally, it has provided valuable information about the cosmic microwave background, a radiation leftover from the universe's early days. According to the Lambda CDM model, as we look back in time and across vast cosmic distances, the galaxies we observe should appear smaller, bluer, less developed, and with fewer heavy elements. This predictive framework guides our exploration of the cosmos, offering a way to understand the evolution of galaxies over cosmic epochs. The model predicts the existence of a period called the Dark Ages, a time when there were no visible stars or galaxies, but this era is currently beyond our observational reach. Despite the success of the Lambda CDM model, there are challenges. Some observations and data don't perfectly fit its predictions, leading to a crisis in cosmology. Theoretical predictions of the model don't align seamlessly with empirical data, creating doubts about our understanding of the universe's fundamental mechanisms. These discrepancies show up in unexpected cosmic structures, irregularities in the distribution and behavior of cosmic elements, and anomalies in the patterns of the cosmic microwave background. These inconsistencies question the model's ability to provide a comprehensive explanation for the observed universe, prompting a reevaluation of our current understanding of cosmic evolution and structure. Now, if that hasn't provoked your interest, brace yourself to uncover what scientists are saying about these cosmic mysteries. The universe's age through different lenses. The universe is full of mysteries that even really smart people can't solve. One of these mysteries is figuring out how old the universe is. Scientists who study space face a challenge because they use different methods to measure the universe's age, and these methods often yield different answers. They are working hard to understand why these variations exist. One approach scientists take is examining the radiation left over from the universe's inception. This radiation contains clues about the early stages of the universe. Scientists employ mathematical principles and ideas from Einstein to decode these clues, helping them comprehend the universe's composition. They establish connections between elements like dark matter, dark energy, and radiation to understand how the universe's growth rate changes over time. To determine the universe's age, scientists rely on crucial tools such as the cosmic microwave background, a remnant from the universe's early formation. Special maps created from space missions provide detailed information about the universe's state during its nascent phase. However, there's a challenge. These maps lack substantial information about something called dark energy, which may not have been significant in the early universe. Consequently, scientists must deduce the effects of dark energy using alternative sources of information. Despite this limitation, scientists utilize Friedmann equations to calculate the universe's expansion rate at different points in time. This not only helps them comprehend the current rate of expansion, but also enables them to reconstruct the universe's growth over an extended period. Through these calculations, scientists can estimate the current age of the universe. Another way to determine the age of the universe involves studying a fascinating occurrence in space known as Type 1 supernovae. While the cosmic microwave background provides insight into the state of the universe billions of years ago, observing the current expansion of the universe serves as an alternative method. Type 1 supernovae can be likened to celestial spectacles, resembling cosmic dramas where a star transfers some of its material to a nearby white dwarf, leading to a powerful explosion. These explosions, occurring uniformly throughout the universe, act as significant reference points for scientists. They are referred to as standard candles, signifying that scientists have a reliable understanding of their expected brightness. This knowledge serves as a crucial tool for estimating the rate at which the universe was expanding during the instances of these explosions. Scientists gain valuable insights by comparing the anticipated brightness of Type 1 supernovae with their observed brightness. This comparative analysis aids in comprehending the varying expansion rates of the universe at different points in its history. This scientific approach originated in the late 1800s and played a pivotal role in uncovering information about dark energy, a mysterious force influencing the universe's appearance. Over time, it has evolved into a highly significant method for measuring and investigating the dynamic growth and transformation of the universe. The Hubble constant is a tool that helps us measure how much the universe has been stretching since the Big Bang, which occurred about 13.8 billion years ago. Imagine the universe as a balloon expanding, but not at a constant rate. It's not just growing, it's accelerating, like a car gradually speeding up on a highway. NASA's research in this field goes beyond determining the speed of this expansion. They're also investigating what could be causing it. If the expansion is slowing down, it might be due to something mysterious, like dark matter acting as a brake. On the other hand, if the expansion is speeding up, it could be attributed to something called dark energy, essentially pushing on the accelerator. Now, let's dive into the telescopic detective work unraveling this mystery. Anomalies in the universe's expansion rate. In January 2018, scientists made a fascinating discovery. When they peered through powerful telescopes, they observed that the expansion rate wasn't uniform across the universe. The Hubble Space Telescope and the Gaia Space Telescope detected a faster expansion in the nearby universe, while the Planck telescope observed a slightly slower expansion in the more distant regions. The Hubble Space Telescope, named after Edwin Hubble, owes its name to the American astronomer who initially proposed the concept of an expanding universe. In 1929, Hubble was studying galaxies, particularly those located far from our Milky Way. He noticed a groundbreaking phenomenon. As galaxies increased in distance from us, they appeared to move away at a faster pace. In the beginning, scientists believed that galaxies were simply drifting apart. However, with time, they came to a more profound realization. The entire universe itself was expanding. Imagine it as if you were on a colossal elastic rubber sheet. Regardless of your location on this sheet, everything around you appears to be moving away. Furthermore, the more distant an object is, the faster it appears to be receding. This breakthrough fundamentally altered our perception of the universe. It's akin to solving an enormous puzzle where every element, from the tiniest atoms to the immense galaxies, contributes to the incredible narrative of expansion. What adds an extra layer of complexity and fascination is the realization that this expansion is not uniform throughout the universe, making the quest to comprehend the cosmos even more complex. Hubble, with the information available in his time, made educated guesses about the universe. However, our technology has advanced significantly since then. Telescopes like Hubble and Gaia act as cosmic detectives, continually observing and refining their methods of measurement. While some telescopes utilize cosmic microwave background radiation to determine the Hubble constant, this approach has limitations, especially in studying distant supernovas, making our understanding of the remote universe somewhat unclear. Since the discovery of dark energy 2 decades ago, scientists have faced challenges in reconciling different measurements. Debates arise on significant topics like the age of the universe and its rate of expansion. Despite our improved technology providing more accurate results, it also highlights discrepancies in our understanding. Efforts to address these disagreements by employing even more advanced technology lead to additional questions about the fundamental workings of the universe. Although the variations may seem minor, like 10 to 20 million years in a universe approximately 13.77 billion years old, they carry substantial implications. Resolving these disparities poses a complex puzzle. One hypothesis suggests potential errors in measuring the cosmic microwave background, yet tools like the Planck satellite, responsible for this data, have undergone extensive verification since their release in 2013. Another intriguing idea proposes that our understanding of dark energy might be incomplete. Dark energy could be dynamic, changing over time, potentially interacting with dark matter or involving unknown elements. Scientists find this prospect fascinating, generating numerous papers and theories in an attempt to unravel this cosmic mystery. Scientists are trying hard to figure out how the basic forces in the universe operate. The discrepancies in measurements are challenging our current knowledge, encouraging scientists to create new theories and experiments. Investigating the potential connections between dark energy, dark matter, and other elements opens up various possibilities, providing insight into how the universe evolves over time. It's not easy to use exploding stars to measure the universe's growth rate. Understanding these explosions is complicated, making the measurements tricky. If we don't fully grasp the physics of exploding stars, it becomes challenging to rely on them as accurate tools for understanding the universe. Even a small mistake in modeling exploding stars could explain the significant differences we observe in the universe's growth rate. The James Webb Space Telescope was expected to revolutionize our understanding of space, tackling topics like dark energy, dark matter, and the universe's expansion speed. However, instead of bringing clarity, the telescope's detailed observations have added complexity to the situation. Bridging the gap with new observations. Hubble discovered that the universe is getting bigger by observing galaxies. The James Webb Space Telescope, however, has created a challenge by showing us pictures of galaxies forming much earlier than we expected. This challenge revolves around understanding how galaxies form, their connection to age and redshift. According to our usual understanding, hydrogen, a crucial element, started showing up about 400,000 years after the Big Bang when protons and electrons joined. Before this, protons and electrons coexisted with what would later become the cosmic microwave background radiation. After hydrogen formed, the universe had mostly a smooth gas of these atoms, mixed with helium and some background radiation. In this setting, gravity could work in denser regions of the hydrogen gas. These denser areas slowly collapsed, giving rise to the first stars in the universe. These early stars were mainly composed of helium and hydrogen, the fundamental building blocks of that era. But a significant change was about to happen. The stars underwent a process called nuclear fusion, allowing the creation of heavier elements such as carbon and nitrogen. These new elements played a vital role in forming galaxies as they absorbed heat and emitted cooling light. This process helped gas come together to create the vast cosmic structures we observe today. As the first stars in the universe ended their lives and exploded, they spread heavy elements into the surrounding gas. Each explosion, along with emerging black holes, released ultraviolet radiation that removed electrons from hydrogen atoms, making the universe more transparent to UV light. New generations of stars continued this process, gradually filling the universe with heavy elements and UV radiation. Eventually, these elements and radiation reached levels that allowed large amounts of gas to come together and form galaxies. These galaxies became strong centers of gravity where gas collapsed, creating stars and other cosmic objects. While what we observe supports much of this story, there are challenges when we try to fit it into the bigger picture of an expanding universe. Figuring out how the early formation of galaxies, the birth of stars, and the overall evolution of the cosmos fit together is still a complex puzzle. It's a significant challenge for scientists studying space, urging them to improve and reconsider our current models to better explain these observations and understand their implications for the universe. The usual model we use in space science is crucial because it links the distances we observe in space to how much time has passed since the Big Bang. These distances are usually considered fixed, straightforward values. However, the age we figure out is based on ideas about how the universe is getting bigger. This idea relies on Einstein's general relativity and our knowledge of matter from particle physics. It helps us grasp how the distance or redshift is connected to the time since the universe began, the Big Bang. But when the James Webb Space Telescope started peering deep into space and studying distant galaxies, it found things that don't match what we currently understand. Specifically, It discovered galaxies much farther away and older than the standard model predicts. Although hints of this mismatch were noticed before by the Hubble telescope, the James Webb Space Telescope clarified these discoveries. The main issue is that the age of the earliest galaxies doesn't align with what the standard model anticipates based on the redshift. The new galaxies we've observed seem to have appeared much earlier in the universe's history than expected. This conflicts with the timeline we've established based on their distance from us. According to our current models, these galaxies shouldn't have formed so early in the cosmos. This contradiction suggests that we might be overlooking some crucial elements in our understanding of how galaxies came to exist and transformed in the early universe. The main idea of the Big Bang theory, which suggests that the universe is always transforming, is still accepted. However, with new information emerging, scientists are re-evaluating and enhancing our understanding. The big question is, how much of our current knowledge needs adjustments, and what are scientists doing to explore these mysteries further? To solve these complex puzzles, scientists are using more advanced tools and methods to address significant cosmic questions. One notable effort in this exploration is the Flamingo Project, a part of the Virgo Consortium. The role of regular matter and dark matter. The Flamingo Project employs highly detailed computer simulations to track the universe's changes from its beginning until now. It's a substantial undertaking to comprehend the evolution of everything in the cosmos. Funding for this project comes from respected organizations such as the European Research Council, the UK's Science and Technology Facilities Council, the Netherlands Organization for Scientific Research, and the Swiss National Science Foundation. These simulations generate virtual galaxies and clusters, aiding our understanding of how cosmic structures may have evolved over billions of years. Simultaneously, advanced telescopes like the Euclid Space Telescope and NASA's James Webb Space Telescope continue to collect crucial information about celestial objects. The primary aim of these simulations is to compare their data with what these telescopes observe. This comparison helps verify the accuracy of the standard model we use for the cosmos. Scientists aim to determine how well these simulations align with our observations to assess if our model effectively explains the universe's changes over time. Professor Carlos Frank, who plays a key role in Flamingo research and teaches fundamental physics at Durham University, talks about a crucial moment in cosmology. Right now, the information from new telescopes doesn't perfectly match what our existing theories predict. This difference makes us wonder if our theories are right or if there are biases in them. To handle this, it's important to create accurate computer simulations. In the past, simulations mainly focused on cold dark matter, but now, astronomers are paying more attention to including regular matter and neutrinos, which make up only 16% of the universe. This helps us understand cosmic evolution more precisely. Led by Professor Joep Schea from Leiden University, researchers conducted many simulations to study how the universe changes. They used a powerful computer named Cosma 8 at the UK's DRAC high-performance computing facility. These simulations ran continuously for over 2 years. The main goal was to understand the effects of both dark matter and regular matter, with a special focus on the role of regular matter. These simulations were complicated and required a huge amount of computing power, about 50 million hours of processor time. To handle this workload, the researchers created a new code called Swift. This code was crucial because it distributed the computing tasks across thousands of processors, making the simulations run smoothly and effectively. At times, up to 65,000 processors were used, highlighting the large and complex computing setup needed to deeply study cosmic evolution. It might feel a bit strange when our knowledge about the universe goes through a major shift. However, if we look back at history, we see that our understanding of science has always changed and improved over time. The way humans view the cosmos has transformed significantly throughout history. Initially, people believed that Earth was the center of everything, with stars and planets revolving around it. This notion stuck until the 16th century, when Nicholas Copernicus challenged it. He proposed a new model, where Earth and other planets orbit the Sun, altering our perception of celestial motion. In the late 17th century, Isaac Newton made another significant contribution by explaining the forces, especially gravity, that govern planetary movement. This greatly advanced our comprehension of the universe. As the 20th century began, Albert Einstein introduced his general theory of relativity, which brought about yet another paradigm shift. This theory described space and time as interconnected, revolutionizing our understanding of gravity. In 1915, Einstein suggested that gravity occurs because mass warps the nature of space-time. Think of it like a heavy object creating a dent in a sheet. The larger the object, the more the sheet curves around it. This curvature not only affects objects, but also alters the path of light. In the presence of a massive object, even light follows curved trajectories because the object bends the space itself. This concept, known as gravitational lensing, played a crucial role in Einstein's gravity theory. A well-known scientist, John Wheeler, once explained a complex idea in a simple way. Stuff makes space bend, and space tells stuff how to go. This idea helps us understand the deep connection between physical objects and how space is shaped, revealing how the mass of objects influences the universe's fundamental structure. This link between the material world and the curvature of space guides the complex dance of celestial bodies in our cosmos. This bending of space doesn't just impact physical objects, it also alters the trajectory of light. Imagine a straight line on a flat piece of paper. When the paper bends, the line is no longer straight. Similarly, when light travels through curved space, its path, called a geodesic, can bend. This bending of light around regions where space is curved by massive objects is what we refer to as gravitational lensing. But how important is the role of gravitational lensing in not just supporting, but cementing Einstein's daring theory of general relativity? The endless universe without clear boundaries. You see, before Einstein's groundbreaking theory, Isaac Newton portrayed space and time as unchanging backdrops for events. Although Newton did predict some light bending, Einstein's notion of a dynamic, changing space faced skepticism and required strong evidence for acceptance in the early 1900s. Gravitational lensing, both observed and predicted, played a crucial role in substantiating Einstein's theory, known as general relativity. In the early 1900s, debates raged over whether the Milky Way constituted the entire universe or was just one of numerous star clusters. Edwin Hubble contributed to this discourse by determining the distance to a hazy object beyond our galaxy. His calculations demonstrated that our galaxy is merely a fragment of an expansive universe. Utilizing Einstein's insights, Hubble also discerned that distant galaxies were moving away from us. This revelation provided compelling evidence for the expanding nature of the universe. The Hubble Space Telescope, even though it wasn't directly named after Edwin Hubble, played a significant role in making these measurements better. It's a very important tool that scientists use to study and explore the universe. Moving ahead in time, Stephen Hawking, who is a really respected scientist, came up with an interesting idea. He suggested that even though the universe might not go on forever, it doesn't have a definite edge, kind of like how the Earth's surface doesn't have a clear end point. Hawking also thought about different ways the universe could come to an end, which made us think more deeply about space and what might happen to it in the end. His ideas made us consider new things about the universe and what might happen to it eventually. In the vast space filled with stars and galaxies, there's a complicated puzzle known as the S8 tension. This challenge in the study of the universe is about understanding how evenly everything is arranged and dealing with uncertainties about its structure. Despite the breathtaking beauty of the sky, we're still not sure about how stuff is spread across space. leading to this puzzle called the S8 tension. This tension arises from differences in our cosmic information, especially in how things are arranged in today's universe. Scientists are trying to solve this puzzle using a new computer simulation called Flamingo. Unlike older simulations that mainly focused on dark matter, Flamingo also considers regular matter and how its gravity affects the development of everything in space. The way the universe is shaped, known as the S8 parameter, is a big puzzle for astronomers. They want to figure out this parameter accurately by looking at events with low redshift, such as surveys that study weak gravitational lensing. Gravitational lensing happens when mass bends spacetime, helping scientists observe faraway objects. However, there's a hitch. The S8 values obtained from cosmic microwave background experiments don't match those from studies on gravitational lensing. The cosmic microwave background suggests a higher S8 value, creating what we call the S8 tension. This problem is distinct from the Hubble tension, which deals with disagreements about how fast the universe is expanding. The S8 tension is a brand new challenge in the field of cosmology. Even though we use detailed simulations like Flamingo to understand how regular matter, including extreme things like galactic winds, influences the universe, we're stuck with the S8 tension problem. We're uncertain about the origin of this issue. Some possibilities have been suggested, ranging from errors in measurements to the need to reconsider our entire theory of gravity. Simulations have revealed something perplexing. At low redshifts, the universe appears less uneven than expected, challenging the predictions of the standard model. However, certain measurements between low redshifts and the CMB align perfectly with the standard model, indicating that the universe might have undergone significant changes over time. This intriguing notion proposes that the universe might have initially followed our expectations before experiencing a major transformation. It's possible that our current model still works to some extent, but we may need to adjust it to align with these new observations. Scientists are diligently working to determine the extent of the changes needed in our model, striking a balance between what we already know and what we're discovering about the evolution of the universe. If you enjoyed this video, give it a thumbs up, drop a comment below, and hit that subscribe button for more content like this.